Hi there, and welcome to the FSC's NEA Student E-Conference. So this is video number 2 in our Student E-Conference, and this one is all focused on physical geoskills. So we really hope that this is useful in building those skills and knowledge that you are going to need to help tackle your independent investigation. So how this is going to work is that we've got a video for you. It will last around kind of 45 minutes or so. At the end of the video, there is an opportunity to, we're going to be answering some questions. So I'll bring back our presenter of our video and myself. And what we'll be doing is we'll be answering some of the questions. So if you do have any questions that you would like to submit to us to answer later on in the conference, you can send them to us at questions@fieldstudiescouncil.org, and in between those words there's hyphen, so it's questions@fieldstudiescouncil.org. So during today's video, you're going to have be introduced to lots and lots of different physical fieldwork methods. What's really important is there's going to be lots of information in this video, so we would like to kind of help you, I guess, with making some of those notes. If you're scribbling down at home, really thinking about how you might take some of the messaging from this. So I've got this little thing which I think has got some top tips that if I was structuring my notes from today's video, I would like to focus on purpose of each of the methods. I'd also like to be focusing on justification of those methods. So why are they appropriate? Then thinking about both the advantages and disadvantages of those methods. Really thinking about how I might adapt some of those methods. So where are there opportunities to change some of the methodology? Maybe thinking about how they could be adapted in different environments. Always thinking about how I might use those methods safely, so thinking about risk assessment, and also thinking about any ethical considerations that I might need to be making. And all the way as well with all of these methods, really thinking about how sampling can play a role as well. So thinking about sample size, sample strategy. So you might find it useful to maybe draw up a little table to help you capture some of the learning that will be happening within this video. So I'm going to come off the screen now and I'm going to play our video. So I hope it's useful for you. And I'll see you at the end. Don't forget, you can submit questions to us at questions@fieldstudiescouncil.org with the hyphens between field and studies and council. Enjoy the video.
Hello, my name's Jo. Welcome to sunny Suffolk here. I'm at Flatford Mill. This is the Physical Skills Technique video from the FSC and GA as part of their student learning videos from the 2020 E-Conference. Our aim is to build the skills and independence that you will need as A-level geographers in order to be able to prepare for your independent investigation. Over the next 45 minutes, we hope to achieve the following objectives. Firstly, we'd like to introduce you to some key techniques that are going to be able to be used in a physical environment. Secondly, we'd like to build your confidence in considering how you might adapt those techniques and make them more suitable to your own investigation. And thirdly, we'd like to develop an understanding of things like sampling, sampling size and ethics, all of which are really important in physical investigations. I really hope you enjoy this video. When we're considering physical skills, we may be choosing fieldwork methods that can help us to investigate topics such as coasts, ecosystems, water and carbon. It may therefore be useful when planning initially to think about a systems approach. This will ensure that you have a holistic, big picture to think about these environments in that context. For example, in an investigation into the hydrological cycle within a catchment or a drainage basin, you might consider the inputs, precipitation, the transfers, overland flow, channel flow, infiltration and percolation, and the stores, groundwater stores and surface stores. Whereas if you are looking at a coastal investigation, say within a stretch of coastline, you might consider systems such as sediment cells, and processes such as erosion, transportation and deposition. You'd also think about how those processes affect the features and landscape in that area. You might also then go on to think about the management and how it affects all of those processes, features and landforms, as well as how it impacts on people. First, we will look at the various ways in which we can measure vegetation, abiotic and soil conditions within carbon investigations or ecosystem investigations. In your chosen investigation, there may be a need to study vegetation and the surrounding conditions within a physical environment. First, we're going to look at assessing abundance. A quadrat is often used to assess abundance of vegetation cover, as it gives us a standardised area in which to sample, which allows us to collect reliable data. There are many different ways of doing this, and your job is to justify the most appropriate method based on your investigation and the environment. There are three types of quadrats that we'll look at today: an open frame quadrat on the right, a gridded frame quadrat on the left, and a point frame quadrat in the middle. These all have their merits in different situations and for different uses. The frequency of a single species is most easily measured in an open frame quadrat, like this one, as it gives us a standardised area to assess, but without any obstructions to cause us to miss plants. For example, if you wanted to compare the frequency of, say, an indicator species in 2 or more areas, this would be a good measurement to make. The positives are that it's quick and easy and reliable, as we are using an objective value. For example, if we were counting buttercups, like this leaf here, there are a distinct number of buttercups in that quadrat. There is a right or wrong answer, so an objective value will give us more reliable results. The negatives are that it becomes really hard to be accurate if the density is high. If instead of buttercups I suggested that we count the frequency of grass, it would be impossible to know that we had the correct answer, because the grass is growing everywhere and in dense patches. If instead we wanted to assess abundance of more than one species, for example total vegetation cover, or the density of our single species was very high, then frequency would not be a feasible measurement. So we could start to think about other uses of assessment of abundance, like percentage cover. If you look into an open frame quadrat, it would be really hard to estimate accurately the percentage cover of any given plant. So we can increase the precision of our measurement by using the gridded frame quadrat. This gridded frame has 25 squares, so each square is worth 4%. This will increase our reliability of our measurements and therefore the accuracy of our results. So say for example we were looking at footpath erosion, we could decide how many of the squares, 4% each, were bare soil and how many were covered in vegetation. And this would allow us to compare the erosion on different areas of footpath. What if, however, we wanted to look at plants that were taller or very densely packed, say on a salt marsh, a sand dune, or on a grassland edge like this? We would really struggle to use a frame quadrat, as it would squash all of the plants down and we wouldn't be able to see accurately what was underneath. This would lead to us underestimating what was there. This is where the point frame quadrat comes in. This quadrat can look at vertical as well as horizontal abundance, and therefore can be useful in areas of long grass. We can use this quadrat to record point frequency by dropping the pins through the 10 holes along the top and recording the species that touch each one. This tells us what is at each of the points. This can then be converted into percentage frequency. So for example, if you touched 2 buttercups out of your 10 pins, then you have a 20% frequency of buttercups. However, as the pins are very, very small, you need to do many, many pin drops in order to get a representative sample. You might also want to think about turning your point frame quadrat around so that you're covering more of a square area rather than just a linear line. The positive of this method, as said, is that you can use it in long vegetation to record all of the different layers. Also, you can record point frequency, which is an objective measurement and therefore reduces any subjectivity. The downside is, as the pins are very small, you can miss tiny plants that are in between each of the measurements. Or if you have plants growing along the ground, like trailing plants, you may end up catching them more than once. And this would cause you to overestimate the percentage frequency of individual plants. Overall, each of these quadrats has its uses. It would be up to you to justify which one, if any, would be appropriate to use for your investigation. Maybe you wouldn't use any of these quadrats for this purpose and use them for something else. We have known a student in the past who used a frame quadrat and covered it with vegetation and measured the amount of interception coming through. So quadrats, although normally used for assessing abundance, can be useful tools for other things. Remember, in order to show independence in your investigation, it's really important to adapt things from what you've seen in order to make them suitable for your requirements. If we're looking at vegetation sampling, we also need to consider the abiotic environment. That's the non-living physical factors in an environment. Measuring abiotic factors can be really important to a physical investigation. Factors such as wind speed, temperature, light intensity, humidity, they're all going to affect how plants grow and also influence the characteristics of an environment or a physical location. Often, primary data sources of abiotic measurements are just a snapshot in time, what they're like at that particular moment. So it's really important to use secondary data and consider how that might enable us to get more temporal sampling and therefore increase the reliability of our findings. For example, taking the wind speed measurements in a particular location where you're sampling on the day that you're sampling is really important. But being able to back that up with a wind rose diagram from the nearest Met pen would be invaluable in increasing the effectiveness of your conclusions. Making measurements of factors such as light, wind speed, humidity and temperature are really important that we get the sampling sizes right. As you can see, if I take the lid off of our light meter here, we can see a recording that is ever changing. This is because the clouds are moving, there's trees in the way which are moving in the breeze, and we're not going to get a standardised result. So you might consider waiting for 30 seconds or a minute and pressing hold, and then that will give you a measurement. Now, is that measurement the correct measurement for now? Well, how do we know? What we would need to do is to take multiple measurements over a time frame and allow ourselves to get an average which would even out any particularly high or low values. The same is true for temperature and humidity. We can use a hygrometer like this to measure them both, but if we just measure it once, we're only getting that really short snapshot in time. Actually, we should be measuring, say, maybe 10 times over the course of an hour and taking an average. We should also maybe consider measuring in the morning, the afternoon and the evening so that we can see what happens throughout the day. Wind speed is particularly difficult because the wind doesn't spend a constant amount of time blowing in any one direction. Gusts of wind can make it difficult to get reliable results. So taking an average over a minute and repeating this measurement again and again in the same place can give you access to an average that will give you a more reliable result. Edaphic factors, which are factors that are related to soil, are also important to consider, because whilst abiotic factors might give us a snapshot into the current conditions, factors such as soil pH and soil moisture can give us information that ensures we understand what the conditions are like long term for growth of any plants. Calculating pH can be done fairly simply using an in-field pH test kit like this. So here we have a test kit which allows us to take a sample of the soil, mix it with barium sulfate, which stops it from sticking together, put in deionized water and then pH indicator solution. This will give us a solution that is, in this case, green, and we can use that on our colour chart to indicate what we think the pH is. We can also take a sample of the soil and make up a solution with deionized water, and then use one of these digital pH probes to measure the pH of the resulting solution. So the digital probe is more precise because it records to 0.1 of a pH scale, and it's also more reliable because it's a quantitative measurement rather than the colour code chart here, which could be subjective. However, with this, you need to understand that you're only testing the solution, so you might not get as fully rounded a view of the pH of the soil as you would with this one, where you're directly testing the soil pH. Soil moisture can be calculated both relatively and absolutely. So if we just use a relative measurement, we can use one of these, which is a common garden centre purchase, a moisture meter, and you just put it into the ground and it reads off on a relative scale of 1 to 10, 1 being the most dry and 10 being the most wet. So that can give you an easy comparison to make between two areas. However, obviously it is a completely subjective scale. There's not a lot of precision there, and we have no real quantifiable measurement. We haven't got a true absolute value. So if we wanted to have that absolute value, then we would need to take soil samples, and you take your soil samples back to a lab at school. Try not to use your mum's kitchen, she won't be very impressed, but you take them to a lab at school and you can weigh the soil, then dry it and then re-weigh it, and that will allow you to calculate the amount of water that's been lost, and therefore you can work out the soil moisture as a percentage of the dry weight. So in terms of drying, it just needs to go into the oven on a low heat, about 100 degrees for a kind of 4-hour period. Alternatively, you can put it in the microwave for 10 minutes and you leave in a control crucible with some water in it so that you know that the moisture has all been evaporated away. So if you are using this method, just keep safe, make sure you ask permission, and as I say, use an area that is designated for science experiments and not cooking. So the absolute measurement will be more precise. It will also be more reliable because we should have that kind of quantifiable measurement that we're doing the same thing every time. We should get more reliable views. Again, in terms of sample size, there's no point in just taking one measurement of soil moisture. You would need to collect quite a lot of soil samples from each area, so have repeated measurements from each area, so that you can then take an average and have a true comparison between the two areas that you're looking at, or the multiple areas that you want to consider. So we've covered various ways of measuring the environment. We've looked at vegetation analysis, we've looked at soil analysis, and we've looked at abiotics. So the next thing we're going to start to think about is how we might start to consider measuring sediments. Performing sediment analysis can be a really useful tool within a coastal investigation, maybe considering the impacts of longshore drift or the effectiveness of coastal management strategies, or an individual sea defence. There are many ways of measuring sediments, and we're going to cover a few here. But remember, justifying the ones you choose and how relevant they are for your investigation is the most important skill. One measurement that we can make is axis length. Measuring the axis can tell us about the size of our sediments. So for example, we might look at the size of sediments at one end of a bay and monitor them as we go round the bay to see if longshore drift is having an effect on the size of the pebbles. Each pebble has 3 axes, shown here in the diagram, with A being the longest length. Now it's great to measure all 3 to give the most accurate view of the overall size. But to save time so that you can collect lots of repeats and therefore increase the reliability, you might choose to measure just one. If we are going to measure just one, we would choose to measure the longest axes because it's the most easily identifiable. In order to measure the longest length of our pebble, you might consider using a ruler. We'd measure it in millimetres because they're more precise than centimetres, but even with a ruler this brings up problems. As you might be able to see as I hold this close to the screen, measuring a 3D object with a 2D ruler means that we have to estimate where the pebble begins and where it ends. So we have an error creeping in, which means that our precision is low and we're likely to get unreliable results. So instead, we could use a pair of calipers. These calipers are more precise than the ruler because they measure to 0.05 of a millimetre, but most importantly, we can open the calipers and close them around the edge of the stone. This means that we're getting a more 3D measurement, so we're actually kind of looking at the actual measurement rather than an estimation. So reading this, we can look at the length of our pebble as being 34.85 millimetres. If we measured it with the ruler, then the best estimate we can have is somewhere between 38 and 35. So overall, this is a more precise and therefore will give us more reliable set of data. We might find that the sediments that we collect are too small to measure with a pair of calipers. For example, if we were looking at fine shingles, coarse sands and clays to see where the tide has deposited different sediments on ridges or berms, we wouldn't be able to measure them, but we don't want to exclude them because that would reduce the accuracy of our overall results. So we can use the Wentworth scale. So the Wentworth scale shown here allows us to see different sizes of sediments, even though you can't necessarily measure them all. It uses sizes in millimetres or nanometres, and we can work out which sediments we have by using sieves. So for example, we could measure by weight the amount of sediments in different sections. So if we measured through this 4mm sieve, what we would find is caught in there are pebbles and above, because the Wentworth scale tells us that above 4mm we have pebbles. So we could then measure those to see which category they go in using the scale. For very small measurements, we might want to then use a smaller sieve. So this 1mm sieve is going to show us what sands we've got. So as you see, as I tip it through, you'll see sands coming out the bottom. Okay, so we could then start to see the coarse sands that we've caught, and then maybe you've got finer sands that you could use finer mesh sieves to measure. So you'd want to weigh the total weight of the sediments in each category, and that can give you an idea of which types of sediments that you've got. So the pros of the Wentworth scale are that it's a really well researched and well defined scale. So we've got a precise scale to work with, and everyone's doing the same thing, so you're going to get reliable results. It's objective because either the sand or the grain or whatever will go through the mesh or it won't, and therefore we can weigh them and know that we're getting an absolute answer. The downside is it takes quite a long time to continuously sieve all of the different sediment sizes, and you need quite a lot of different sediment sieves, otherwise you're kind of having to estimate between them. So it can be quite time consuming, which means that you might not get enough time to make lots of measurements to get your reliable and representative data sets. We've talked quite a lot about measuring the size of sediments, but it's not just size that is affected by coastal processes. So actually shape is really important as well. So probably the simplest way to define the shape of a sediment is to use the Powers Roundness Index, which you can see here. So the Powers Roundness Index is a qualitative scale where you look at your pebble shape by comparing it to the shapes on the drawing. So if, for example, we look at the pebble that we had earlier, the options we have are very angular, angular, subangular, sub-rounded, rounded and well-rounded. And if we look at the picture trying to match these, this is a pretty well-rounded pebble. So I would say it's up this end on the well-rounded section. So even though it's not a sphere, it is round on every edge, and we define it as well-rounded. However, if we were to look at this pebble here, so slightly different shape, so this one has quite a lot of jagged edges, and although it does have one smooth side, most of it is quite pointy. So we're going to say that that is a subangular pebble. Now, you might already have thought about the fact that this is a nice, quick, easy and simple comparison to make, and you can do it very quickly, so you can cover lots of pebbles in a short space of time. However, the downside is, because it's qualitative, it's therefore quite subjective. So what you might think is a subangular, I might think is an angular, someone else might think is sub-rounded. So we're going to end up with a reduction in the reliability of our results, because there's not a very high precision, because we're making an estimate and personal bias is going to come into our answer. So one way of getting around that is you might have the same person doing it every time, or you might have a collective group and you have to come to a decision based on sort of voting or something like that. However you justify it, it's a good method to use, but you need to be able to say how you're kind of getting around that subjective nature of the scale. As the Powers Roundness Index is quite subjective, we can start to think about different ways in order to reduce that subjectivity and make a more objective measurement. The Zings Classification is one way of doing this, because it looks at the actual shape rather than the roundness, and it uses those three measurements of axes A, B and C in order to classify the shape of the different sediments. So you can see here, the Zings Classification decides whether you have got a rod, a sphere, a blade or a disc, and that is based on those three calculations, looking at the different measurements of the axes. So for example, a sphere, if you divide axis B by axis A, you need to have an answer of above 0.67. And if you divide axis C by axis B, you have a value of 0.67 or above, and that will give you a sphere. So let's have a go to show how this works. So if I show you a pebble here and we make those measurements, so the measurement of the A axis, so that's our length, is, I am going to round up here to make the maths easier for myself. So that's a measurement of 20 millimeters. And then we're going to measure axis B. And we've got 11 millimeters. And then axis C, we've got 7 millimeters. So if we go back to our example, if we're looking at this category, B divided by A, then we've got 11 divided by 20, which gives us 0.55. So that means it's less than 0.67. So it's going to be either a blade or a rod. Now our other measurement here of C divided by B, 7 divided by 11, so we've got 0.67. 0.64. So again, we are lower than 0.67. So for both of them, we are lower. So that means that this can be described as a blade. So it's long and quite flat. Now what this does is it tells us about how pebbles and sediments are going to move. So for example, a sphere or a rod is going to move much more easily in the waves, needs lower energy in order to move them, because they will roll around very easily. So transportation needs less energy to move them, rather than those blades and the discs. They're going to need more energy to move them because they're flatter, so they're not going to roll. They're going to have to be kind of skipped along the bottom. So this is really interesting because it can start to tell us about the position up the beach that we might find different things, or again around the bay depending on longshore drift. Now, thinking about positives and negatives, positive is with Zings calculation, we've taken away that subjectivity, we've made objective measurements, which means that we're going to have hopefully more precise and reliable data and therefore a more accurate view. And then we've turned that into a qualitative shape, but based on a quantitative measurement. Okay, so using that is really good at giving us precise and accurate view of the shape of these pebbles, and it's also a well-researched and defined scale. So again, we're working to the same thing, so everyone should be getting the same results each time. The negative is it takes quite a long time to measure each of the axes and also to then work out which category it's in. So you would need to maybe have a system of how you did that so it didn't get really confusing. And the last thing to mention is with all of the measurements that we've made in terms of the size of the pebbles and the roundness of the pebbles, when we're thinking of where things are on beaches and what that tells us about the environment, it's really important to remember that there is a possible limitation of human influence, because people love to pick up pebbles and throw them, move them, skim them, build little piles of them. So we have to also take into consideration that not every pebble that we find is in that place because of the way that the sea has moved it. It may well have been put there as part of a sandcastle. So we've talked about environmental variables and also sediment analysis. Now, the last area of physical techniques to consider are methods that are specific towards carbon and water investigations. First, we're going to look at interception, the measurement of how much water is intercepted by vegetation on its way to the ground. This can be really useful as it can help us to form insights into land use management and also flood prevention strategies. So by placing rain gauges under various canopies, this can be really useful to determine the percentage of precipitation that the canopy is going to intercept. If we know the total rainfall that's happened in an area over a specific time, and we can work out how much has got to the ground, then we can get a percentage of interception. So we could use this type of rain gauge to measure the amount of water that's coming through the canopy in millimetres. And we might think about putting this under deciduous trees like this big sycamore behind us here, or we might consider looking at coniferous trees, maybe some pine trees around the area, or maybe we could consider areas of different tree density and how that might affect how much interception is happening, whether the trees are managed, whether they're a natural woodland, and what those different factors are going to do in order to the amount of rain that's falling through. You might even want to consider measuring the canopy. So you can use something called a canopy quadrat in which to do this. Now, with your canopy quadrat, you can see that there's 25 spots on the quadrat, and we can use this to look at point frequency and then calculate percentage frequency. So what we'd need to do is to look up into the canopy through our quadrat, and then we'd be able to see how many of these spots have leaves behind them, and that would allow us to tell the percentage frequency of canopy. And we could then decide where to place our rain gauges based on those differences in different areas. So we need to think about where we're putting our rain gauges, and you might not be able to get your rain gauge to stay in one place underneath your trees, or you might not have many of them. So you can actually just use some small cups, and we've put a few out here. When you come back to empty them, you can then use your rain gauge to measure how much water has been allowed through the canopy. Now you need to think about being representative. How many samples and where are you going to put them in order to get reliable and representative data? We obviously also need to be able to justify this method. So thinking of the strengths, we have a quantifiable method that we can compare to either accurate MET collected data from a nearby MET station, or have a control measure that we keep out in the open that will tell us how much rain is happening in this specific area. So we can get an accurate view of what is happening. However, the weakness is we need quite a few cups out around any given tree to get a reliable sample, because there'll be different densities of branches within the same tree. And also we need to look at more than one tree of each type, because we don't know that this particular sycamore tree is telling us the whole story about sycamore trees in general in this area. Also, you might find a problem with this doing it in summer. As you can see in my cup, there's no rain, and there hasn't been for at least a week. So you'd need to think carefully about when and where you put out your cups.
We might also start to consider stored carbon if you were looking at a carbon investigation. Now this is really useful, as we can start to understand the carbon content of trees in any given area. And this can help us to estimate the carbon storage within an ecosystem, or in different areas of woodland, maybe those under different management regimes. In order to calculate the carbon storage, we need to know the trunk volume to start with. And in order to do that, we've got to make some measurements. So we're going to start making measurements of this big ash tree behind us. To measure the volume of the trunk, we need to know, first of all, the circumference. So we measure the circumference of the tree in meters at around chest height. So we have a circumference here of 1.04 meters. Now we're also going to make some other measurements, and we need to move a bit further away. We're going to make a measurement from my eyes to the top of the tree and record the angle with this clinometer. So this records the angle in degrees, and if I hold it to my eye and look up until I can see the very top of the tree, I have an angle of 66 degrees. Now I also need to know the measurement between my body and the tree in meters. Okay, and I also need to know the measurement from my eyes, where I've created that angle, down to the ground.
We showed you outside how and why you would start to consider measuring carbon storage in trees. Now let's look at the calculations. The first thing we need to do is to work out the volume of the tree trunk, which is officially referred to as the stem. We've taken some measurements in order to do this using a tape measure and a clinometer. These are reminded here for you on the diagram. H is the distance from the ground to the observer's eye in meters. Y is the distance from the stem to the observer. Q is the angle to the top of the stem. And C is the circumference of the stem at chest height. With these measurements, we can start to calculate the volume. Firstly, we work out the height of the stem. We use the equation here to show us how tall the tree is. Next, we can work out the radius. Dividing the circumference by 2 times pi gives us a radius. Finally, we can use these values to work out the volume of the stem. So if we use the equation shown here, which is for that of a cone, we can see the volume of the tree trunk. Now we have the volume of the stem, we need to work out how much of that stem is dry biomass. Some woods are harder than others as they are denser. Therefore, the biomass will depend on the type of wood, i.e. its species, as well as its size. We can use the graph to look at the corresponding biomass for the stem volume of your particular tree. This chart shows the biomass per stem volume for different tree species. Here you can see that for a large deciduous tree like oak, the biomass is higher per volume of trunk than a quick-growing conifer like a larch or a spruce. So you'd need to read off the biomass at the appropriate stem volume that you've calculated for your species of tree. Trees don't only hold carbon in the trunks, however. we also need to consider the canopy and the branches, which we call the crown, and also we could consider the roots. So we need to use different charts to find out more. On this chart you can see the relationship between the diameter at breast height and the crown biomass for different tree species. Just make sure when you're looking at diameter at breast height, you need to have made sure that you multiplied your radius by 2 to get the right calculation. This one shows the biomass in the roots. In a similar way, looking at larger deciduous trees seem to have more biomass in their roots. To get the total biomass in the tree, we can add up the biomass of the trunk, the crown, and the roots. Then, because about 50% of the biomass in trees is carbon bound in organic compounds, we can divide the biomass by 2 to get our carbon content estimate. This will allow us to contrast carbon sequestration properties in different trees, different woodlands, and different ecosystems, as well as comparing various land uses as different carbon stores. All of this would be really interesting and helpful in a carbon investigation.
The last technique that we're going to look at here is infiltration. Now, infiltration rates can be measured as part of a carbon and water investigation or as a coastal investigation. Infiltration rates can tell us about how the movement of water changes through the ground in different areas. So it might be good at looking at different land uses, whether you're looking at arable farmyards and pastoral farms and woodlands, or whether you're considering how the water system might be affected by different management regimes. It's still really interesting to find out. Now, the most simple way to do it is to use a very simple tube like this one, okay, which we call an infiltration ring, but it's just a piece of guttering. And what we want to do is we want to put this into the ground. Now, we normally say into about 2 centimetres, but it would be entirely up to you, and actually maybe you could come up with your own system of working out how to standardise that, but knowing that you're doing it to the same depth each time is really important. So we'd hit the infiltration ring into the ground to our standardised depth. Okay, now this is going to make sure that we get reliable results. The next thing we're going to do is we're going to pour water into the tube very carefully. Try not to pour it down the outsides, because otherwise you'll sort of undermine the side of your tube. So into your tube goes your water, and we're going to fill it right up to the top, and as it gets to the top we're going to press our stopwatch. Okay, now after 1 minute we're going to measure how much water has disappeared from the tube, i.e. how much infiltration there has been in 1 minute, and that can give us a rate. Now we'll measure in millimetres because we want to make sure that we're being as precise as possible. Okay, and we'll measure from the top, because that's where we filled the water to, down to where the water is at our 1 minute point. Now you might consider doing this repeated in the area. Obviously don't do them too close together, because you would end up sort of compromising each of the measurements, but you'd want to make sure that you get a reliable view and a representative view of the area. So we'll just make that measurement now. So we've lost 25 millimetres in our first minute, and so we've got a rate of 25 millimetres per minute. Is that reliable? Well, ideally you'd probably go another minute, okay, and take an average, another minute, take an average as you go, so that you're getting a really precise view of what's happening to the infiltration over time. And then maybe you'd want to consider looking in a different area. So this is a recently cleared area. Maybe we would then consider looking into a grassland or a woodland with lots of coverage. And we start to bring in all of those other things that we've looked at as well, including the interception, okay, because that's obviously going to affect how saturated the ground is, and therefore how much infiltration there's going to be. Now the positive of this method is you're getting a quantifiable result, and it's fairly precise because we can use millimetres per minute as our rate, and we can do it lots of times and get a nice, reliable and representative sample. The downside is if the ground is really hard, which it has been around here, then it's actually very hard to get it into the ground in the first place. And often on the beach, if you're doing this in the clay or the sand, you can spend quite a lot of time trying to get it to work without pouring out of the sides. Because if you do get a leak at the bottom, then obviously you have to start again because you've got an undermined investigation. So overall, it's a useful technique, but it can be quite time consuming and it can be quite hard to do if the weather's been very nice and you've got quite hard ground.
We've managed to cover loads of different techniques in this physical video. Thank you so much for joining us, and I really hope that some of them will be useful for you as you go forward in your independent investigation. Make sure you consider how you can adapt and develop them to suit your own title. I really hope it's been useful as you go forward as well. Make sure that you look at the research tasks and the review tasks that are inside the video. This is going to help you to take this forward and really help you to develop your skills in geography and for your independent investigation. Thanks for joining me. Bye.
Hi there, welcome back. So I hope you really found that video useful, and I'm really pleased to say that I'm joined by my colleague Joe, the expert field tutor who we had in that video. Hi there, Joe.
Hello, how are you?
I'm good, thank you. Thanks so much for putting those videos together. I know you've been out and about all over Suffolk with your camera phone filming. So
Yes, yeah, it was good fun, Bit windy sometimes, but good fun.
Excellent, thank you so much. So my first question before we tackle some of our student questions is, what would be some of your top tips for choosing some physical fieldwork methods?
Okay, so, well, I think mainly you've got to think about validity. That's the most important thing. So is your, whatever question you're asking or however you want to interrogate the physical landscape, is the method that you're choosing going to help you to answer that question? So it's about whether you're going to get a valid set of data, whether it's going to actually be fit for purpose and help you to do what you need to do, because otherwise, obviously, it's probably the wrong way to go. And then once you've thought about that, you need to consider whether you can logistically do it. So whether you've got the right kit, whether you've got the right environment to do that method, and how easy it's going to be logistically so that you can make sure you collect enough data to get a reliable set of information and a representative data set as well. So making sure that you've got repeats in different areas, or that you're covering enough of the area or the population or whatever it is to get a representative view. So those would be my top tips.
Thanks there, Joe. Really good top tips. And actually that will really help with a question that we've had in from Aaliyah. And she's been asking us, just a first question was a reminder of that word we use for soil conditions. So that was edaphic. So those soil conditions, we're really thinking about using the word edaphic and abiotic for those non-living conditions. But Aaliyah's question was what to do if she didn't have access to some of the instruments that we would need to measure some of those abiotic factors. What top tips would you have for Aaliyah there?
So yeah, that is a problem, and especially if you can't access all the things that you want to, then that is going to kind of limit you. But because we want to make sure that everyone's doing the very best that they can for their independent investigation, I would, first of all, I would talk to the science department in your school, because even if the geography department don't have some of those bits of kit, then the science department almost certainly will have things like light meters and temperature probes and things like that. So check with them. If they really don't have anything that you can borrow, then you can try and do a bit of DIY. So I know it sounds kind of silly, but if in the absence of a light meter, you can use kind of canopy cover as a proxy. So we mentioned canopy cover in the video there. And in the video, I used a little just an acetate with a grid or some dots on it. But I have seen students in the past just get like a toilet roll tube and put a bit of cling film over the top of the toilet roll tube and draw a little square on it with grids. So you can literally just look up through the canopy and see how much there is. If you can't make things, or you don't have the capacity to make what you want, then you can often get apps on your phone for things like light and sound and even temperature and things like that. And I know that we don't want to think about buying things or expense of getting things, but you can sometimes get apps that have little like connectors that you put onto your phone, and they can read the wind and all sorts of things. Failing all of those, I'd go with secondary data. So get in touch with your local Met station, and they'll have data that you can use. But obviously it's better to get some on the day if you can.
Lovely. Thanks very much, Jo. Really nice to get your experience there of how students you've seen adapt and overcome when perhaps they don't have that equipment. And sometimes that's absolutely fantastic when we get that adaptation, so key with that methodology. So thanks for that. We've got another question here about, this time it's working in a sand dune environment. So what are some of the ethical considerations of investigating a physical environment such as a sand dune? So what things might you consider from an ethical point of view?
Yeah, so ethical considerations are really important when you're doing any kind of field work. I think if you're considering a sand dune in particular, then I'd go down there's three main things to think about. So firstly, I would think about any plants or animals in that environment. So in a sand dune system, because it is covered in vegetation for a large part of that environment, you just need to think about how you move around the environment. So trying to follow paths that are already established when you can, because you don't want to be putting more pressure on vegetation in terms of trampling, because that can obviously lead to sort of collapses and blowouts in the dunes if you get a lot of pressure on them. So following paths and just making sure that if you are sampling in the vegetation, which obviously you'd want to, you're trying as best you can not to sort of lie down, sunbathe, get your picnic rug out and kind of squash everything. So being as sort of unobtrusive as possible, and as just any animals, check before you go. I know the sand dune system that we use, there's quite a large colony of little terns, which are ground nesting birds. So just checking before you go where those things are, and then completely avoiding them is a really good idea. So animals and plants are one thing. Secondly, in terms of ethical considerations, making sure that you have permission to be there, because ethics doesn't just rely on us not annoying the natural world. We've got to make sure that we don't annoy other people as well. So yeah, permission to be there, making sure it's not a conservation site that has sometimes you get specific times of year when you can and can't do things. So that's a good thing to check. And then lastly, just making sure that you're being aware of other people. In any coastal site, you'll get people sort of enjoying their day. And often if you've got people having their little picnic or having their day on the beach, then they don't necessarily want a load of students kind of trying to measure around them. So again, just being sort of careful with who's there and what's there, and trying to avoid doing any damage whilst you're there.
Thanks, Jo. And what I'd say is quite often there are notice boards up which will guide you as a visitor of how you should be behaving in that environment. And that's a really good starting point, I think, for a student considering ethical considerations, is look for those, because that might guide your behaviour in those environments as well. So thanks for that. We've got another question here, is what secondary data might be useful, or where should we look for secondary data when we're thinking about physical fieldwork investigations? What are some of your top physical investigation methods, secondary data sources?
Oh, good question. Yes, I mean, secondary data is really, really important in any geography investigation. I think it's worth looking at the British Geological Survey website. They've got really great maps of the base rock, the kind of surface rock, and all sorts of, you can really get interactive on the maps and work out what's going on. And they've got really good descriptions of the type of rock. So if you're looking at anything really to do with permeability, infiltration, percolation, any of those things, those would be really useful. Living Atlas on ArcGIS is really good as well, so you can look at different layers there and get information from that. Then you can start to delve a bit deeper, so maybe looking at things like shoreline management plans if you are looking in a coastal investigation, or conservation designation reports. So things like if you've got a SSSI, a site of special scientific interest, then there'll often be an accompanying report as to what's important about it. And METPEN data, as we said as well, weather data, is always easily available. You just got to sort of trawl through it. That is the problem with secondary data, is you need to pinpoint what's important rather than just getting everything. So yeah.
Oh, some really useful sources there. Thanks there, Joe. So we've just got a question come in from Jack, and he would like to know, how do you know if your results are representative of the whole area? And I mean, I think that's such an interesting question, because it's such a fine balance, isn't it, between collecting enough data in the time that you've got, but ensuring that whatever you're collecting is representative. What are some of your justification or kind of understanding of how to know you've got enough data and showing that it's representative?
Yeah, so again, great question. I think in terms of representative sites, you've got to try and think about whether the area you've picked is typical of the rest of those things. So if you take, for example, if you're looking at, like in the example of the trees, if you're looking in a small area of woodland and you wanted to look at, I don't know, carbon content of a particular species of tree, if half the woodland are that species, obviously you want to try and cover a fair chunk of that bit. Just doing one or two is not going to work. Whereas, you might consider, okay, well, actually, I need to get a few smallish trees in that species, a few middle size and a few large ones to get a spread across the kind of a representative view across what's going on. In terms of the number of samples, I think there is no magic number of what the right answer is. It's quite often to think about what you're going to do with the data. So if you're going to use a statistical test to analyze it, then that will determine how many samples you need, or at least often the minimum samples you need. So that's a good indicator. I think there is no right or wrong answer, but you have to be able to justify to yourself that with the time you had, you've done enough to be able to kind of convince an examiner that you've tried to get a good view across the whole of it. So I think, when you think about what the bare minimum is, double that, maybe double it again, and then have a go. But there's no particular answer, I'm afraid, to that one. It's just whether you feel you've covered enough of the area to give a good view.
Thanks, Joe. And I think that bit that you say about ensuring that you've got those minimum samples for any analysis that you're doing is so crucial. So for any of those stats tests, the Spearman's rank, the chi-square, the Mann-Whitney, they do have those minimal sample size that they need. So that's a really good indicator when you're out in the field. And also delving back into some of your maths work, perhaps at GCSE. So cumulative mean, running mean can be a good indicator that you have enough data that's kind of reliable in that sense as well. So thanks for that answer there, Joe. I think we've probably got time for just one more question. And this one was about the differences between quantitative and qualitative data and primary and secondary data. So just as a kind of recap, primary that's the data that you're out collecting yourself. Secondary is the data that you might kind of be looking for other information. So secondary sources, it's already been collected. Quantitative, all to do with numbers, and qualitative is the things that are perhaps written down, photographs, much more descriptive in that sense. And so this question was really focused on what primary and secondary, quantitative and qualitative data there might be around vegetation and abiotics. So we did a little bit of a kind of plot to try and answer this question. So hopefully you can see that up on the screen. So we thought some of the primary data that was quantitative are things like temperature, wind speed, and things that you might collect when you're out and about, perhaps using a data logger. Perhaps some of the more qualitative stuff, qualitative data, to do with abiotics and vegetation might be captured by doing annotated photographs or an annotated field sketch. So that might be some of the stuff that you collect out on the field. And then when it comes to secondary quantitative and qualitative data related to abiotics and vegetation, and we've mentioned it before, but things like MET data, looking at windrows diagrams for those areas that will give you that historic picture of what's been happening in temperature and wind and the climate. And then also from a qualitative point of view is looking for historic photos of an area, perhaps seeing how vegetation might have changed and annotating those, and maybe also looking at some of those ecosystem reports or habitat action plans or SSSI, so sites of special scientific interest citations. There's lots of useful information in those, which will be secondary qualitative information. So hopefully that's helpful for that question about those. So I think just looking at the time, that's probably us done for this evening's Fieldwork Student e-conference on physical geoskills. We really hope it's been useful. Thank you for joining us. This is number 2, so we still have one more video, which will be tomorrow at 4 p.m. And this time we're going to be joined by my colleague Robin, who's going to be looking at human geoskills. So thank you so much for joining us. We hope it's useful. Bye now.
Bye.